In this video, we investigate several more examples of integrating rational functions using a partial fraction decomposition. So for the first example, we have a rational function degree 2 over degree 3. So it is a proper rational function, which means we find the PFD and then use it to integrate. So based upon how the bottom is factored, a single linear term and a repeated linear term, our partial fraction decomposition is going to contain three pieces. We're going to have a over x plus 3 plus b over x minus 1 plus c over x minus 1 squared. And recall that the PFD contains one term, so 3 in this case, for each of the factors of the denominator. X plus 3 is a factor, x minus 1, and x minus 1 squared. To solve for the a and the b, our first step is to take the denominator on the left and multiply by it. And this is going to clear fractions. In the first term on the right, the x plus 3's cancel, and we have a times x minus 1 squared. In the second term, one of the x minus 1's cancel, so x plus 3 times x minus 1. And in the third term, the x minus 1 squared cancels, and we have c times x plus 3. And at this point, we will always plug in intelligent choices of x that allow us to solve for some of the unknown constants. And corresponding to each linear term, so that would be x plus 3, x minus 1, there should be an intelligent choice. So for example, if we plug in x equals 1, the a term and the b term cancel, and we can solve for c. So let's just do that to the side here. If we plug in x equals 1, the left-hand side is going to be 3 minus 8 plus 13. And on the right, you will only have the c term. So c times 4. So 3 minus 8 plus 13 is going to be equal to 8. So 8 equals 4c. So c is equal to 2. Likewise, if we plug in x equals minus 3, the c term and the b term cancel, and that will allow us to solve for a. So plugging in x equals minus 3, we're going to have 3 times minus 3 squared, which is 27, minus 8 times minus 3, so that will be minus a minus, so plus 24, plus 13, and the only term that we are going to have left on the right will be the a term. So when we plug in x equals minus 3, we have a times minus 4 squared. So this is 64 equals 16a, which means that a is equal to 4. So the only term we have left to solve for would be the b term. And in order to do so, what we are going to do is note we have a quadratic on the left, and once we expand everything out, we're going to have a quadratic on the right, and the only way these two things can be equal is if all their corresponding coefficients are equal. So expanding out on the right, we have a multiplied by x squared minus 2x plus 1 plus b times x squared plus 2x minus 3 plus c times x plus 3. And then we can group together all of the corresponding terms. That is, I have one x squared term and a second x squared term. So in terms of the x squareds, we have a plus b. And in this problem, we could stop here. That's actually going to be enough. But I'm going to go ahead and write out the remaining terms as well. So in terms of x, we'll have cx, 2bx, and minus 2ax. And for the constants, we're going to have an a minus 3b plus 3c. And what this needs to be equal to is this original polynomial we had on the left. And note the only possible way this can be true is if all the corresponding coefficients are equal. So for example, the coefficient of x squared on the left is 3, and on the right it is a plus b. So what we need to happen here, in terms of those x squared coefficients, is we need 3 to be equal to a plus b. And looking above, since we already know that a is equal to 4, that means b is going to be equal to minus 1. So it is very useful to plug in those intelligent choices to determine as many values of the constants as we can ahead of time. It makes this last step a bit easier. So now that we've determined the constants a, b, and c, we will have our partial fraction decomposition, and we can integrate. So I've written out the form of our partial fraction decomposition. We can now go through and just anti-differentiate each term individually. So 4 natural log absolute value x plus 3 minus the natural log absolute value x minus 1. And for the last term here, 2 over x minus 1 squared, this will be minus 2 over x minus 1 plus c. And just as an observation for the third integral, when we had 2 over x minus 1 squared, if you did not recognize that antiderivative, no big deal, what we would do is say let u be equal to x minus 1, so that du is dx. And this becomes the integral of 2 over u squared du. And the antiderivative of 1 over u squared is minus 1 over u. So minus 2 times 1 over u. And then substitute back in u equals x minus 1. So let's investigate one last example involving a partial fraction decomposition. In this case, one which involves an irreducible quadratic. So degree 2 over degree 3, it's a proper rational function. So we do the partial fraction decomposition. And the partial fraction decomposition will contain 2 terms, one corresponding to the linear and another corresponding to the irreducible quadratic. So a constant, and then for an irreducible quadratic, it needs to be a constant x plus another constant. So in order to integrate, we need to solve for these unknown constants a, b, and c. And as we've done in the previous 2 examples, we will simply take the denominator on the left and multiply every term by it. The left-hand side is going to be x squared plus 2x minus 4. In the first term on the right, the x minus 1's cancel. So a times x squared plus 1. In the second term on the right, the x squared plus 1 terms cancel. And it's just an x minus 1 with the bx plus c. And as we've mentioned earlier, if you can plug in an intelligent choice to solve for one of the constants, we should always do that. Corresponding to this linear term x minus 1, if we plug in 1 for x, the bx plus c term goes away, and we can solve for a. So just doing a little bit of work to the side. If x is equal to 1, then on the left we have minus 1, and on the right we have 2a. So a is equal to minus 1/2. Now to solve for the bx plus c, we need to expand out on the right, much like we did in the previous example. So ax squared plus a, and then just foiling out the second term, we're going to have a bx squared minus bx plus cx minus c. On the left, we have the quadratic x squared plus 2x minus 4. On the right, if we group together terms, we have a plus b x squared plus c minus b x plus a minus c. So since we know what a is equal to, it's minus 1/2, we should be able to compare the coefficients of the x squared term and then either the x term or the linear term to solve for c. So let's see here, in terms of the x squared coefficients, we have 1 on the left and a plus b on the right. Since a is equal to minus 1/2, that implies b is equal to positive 3/2. And if we go ahead and compare the coefficients of x, we have 2 on the left, and then on the right we have c minus b. Since we know b is equal to 3/2, we know c is going to be equal to 2 plus 3/2. So that would be 7/2. So we now know the values of all three of our unknown constants. And we've seen a very nice technique in this case. When you write out the partial fraction decomposition of something involving an irreducible quadratic, use any of the linear terms to solve for some constants with intelligent choices of x, and then expand out and equate the like coefficients to solve for any of the remaining constants. So let's go ahead and use this partial fraction decomposition to integrate. Now we have three integrals that we need to take care of. And I'm going to break it up into the three separate integrals so the techniques are as clear as possible. So we have minus 1/2 the integral of 1 over x minus 1 plus 3/2 times the integral of x over x squared plus 1 plus 7/2 times the integral of 1 over x squared plus 1. So the value of this first integral, natural log absolute value x minus 1. For the second integral, we have 3/2 multiplied by this integral x over x squared plus 1. So 3/2, and this remaining integral is one we've evaluated several times with a substitution. It's 1/2 natural log absolute value x squared plus 1. Plus 7/2, and the third integral is a common formula, arctangent of x. And because it's an indefinite integral, we finish with a plus c. So note when irreducible quadratics are present, you're going to contain these two integrals. One of them is going to be of the form of constant x over an irreducible quadratic, so typically a substitution will allow us to evaluate. The other is going to be a constant over this irreducible quadratic, which is going to involve comparing to one of our arctangent formulas or completing the square so that we can do a trigonometric substitution.